Welcome to lesson 10.7 for pre-calculus. So today we're going to learn about polar coordinates, something very new and different. So what is the polar coordinate system? I want you to think of a coordinate system like you're used to, where you've got a point and you plot that point using the x distance that is over horizontally and the y distance that is up or down vertically. So think about that system. Now we're going to talk about the polar coordinate system. So instead of x and y, we have r and theta. So r is going to be the directed distance. Directed distance basically means a vector. It is just a segment. It's the length of a segment. It is a segment that has a finite length. Theta is going to be the direction. So in our vectors that we've learned and with our inclination of lines, things like that, where you've now assigned a direction to a line or a vector, that direction is theta. So your polar coordinates have the coordinates r, which is the length of a segment, and theta, which is the direction of a segment. Okay, so this is what the polar coordinate system looks like. It is a gridded system, but instead of it being square and rectangular like our rectangular coordinate system, it is circles. And the reason is because that distance has to be the same distance from the origin at any given point. And as a result of that, that's the definition of a circle. So we're going to have a system that has concentric circles, or circles that are evenly spaced apart. And that's how we're going to plot our directed distance. And then instead of numbers like 1, 2, 3, 4, 5, we're going to have angles. The graph that you have here is done in radians. You can see that we've got pi over 12, pi over 6, pi over 2, pi, things like that. That's the one that the book uses most often. However, you could also have a polar coordinate system where theta is measured in degrees instead. So you'd have like 0 degrees or 30 degrees or 90 degrees. But for this book, we're going to stick with the radian grid. So it's going to be all done in radians. Okay, so things that we need to know. These are very important things. We can have the same point represented in many different ways. Think about the unit circle. When we could have the same point, we could get to the same point on the unit circle by circling around 2 pi. So we have that with the polar coordinate system. So if we take the point r comma theta, so we've got our point right here, r comma theta. If we were to add 2 pi to theta or subtract 2 pi to theta, we would end up at that same exact point. So for example, if we were to say this was our point that we started at right here, and we went around 2 pi, which means the whole entire circle, we'd end up right back at that point. Or if we went the other direction, 2 pi. Or if we went around twice, we end up right back at that point. So when you're dealing with polar coordinates, make sure that you remember that the point r comma theta is going to give you the same point as r comma theta plus or minus 2n pi, where this just tells you n is the number of rotations that you're going around a circle. So 2 pi would be 1 rotation, 2 times 2 pi would be 2 rotations, and so on and so forth. So these are the same point. Now, we also have r comma theta and negative r comma theta plus pi. These are the same point. And this is just a conversion that you're going to want to memorize or put down on your note cards. So they equal each other. And we can write this as an entire equation as r comma theta equals negative r comma theta plus or minus 2n plus 1 pi. So instead of the 2n pi, we have to get the pi by itself. So not an even number in front of it. So we do 2n plus 1 pi. So these are the same points right here. Okay, so let's go ahead and actually plot some of these points. We're going to go on to the next slide. So we've got a bunch of points that we're going to plot. First point that we're going to plot is 3 comma pi over 3. So 3 tells us how far out. So we're going to take each of these circles to be a distance of 1 unit from each other. So we want to go out 3 units. So we go 1, 2, 3. So we are on this circle here. we were to circle this around, this is the circle that we're looking at that has a directed distance of 3, or r equals 3. And we want the point, the angle, to be pi over 3. So looking at our chart, let's move along our circle. We're at pi over 12, pi over 6, pi over 4, pi over 3. Here we go. So that is the point, and it's going to have the directed distance going through here. So we're just going to draw this line that goes through that point with an arrow, but this is actually the point that is on that line. That's the point 3 comma pi over 3. Okay, so now let's move on to the next one. We've got -3 comma pi over 3. So remember from the previous slide, we need to convert this. We need to see what that equals. There's actually a couple of different ways that you could go about this. So one thing that you could do is, instead of going over 3 this way, we can go over -3 this way and down pi over 3 units. So we'd get to there. Or remember our conversion, or what we had written down, is that this is going to equal the point 3 comma, and we're going to add pi to this. So we're going to do pi over 3 plus pi. So that gets us the point 3 comma pi plus pi over 3 is 4 pi over 3. And if we look at the point that I drew down here, we went out to the third circle, so 1, 2, 3, and we can follow our circle around to 4 pi over 3, and that's where we are. So there's 2 different ways that you could plot that point. And again, we're going to draw the line that goes through this, because it's on that line, but it is that particular point. Okay, next one. We've got 3 comma 2 pi over 3. So I'm going to change colors here. And we want 3, so we're still going to go out 3 units, so 1, 2, 3. But we want 2 pi over 3 this time. So we're still in this third circle, so now let's go to 2 pi over 3, and we see that that is right here. So there's our point. It's on this angle line right here, but it's on the third ring. So that would be our point for 3 comma 2 pi over 3. Okay, now we've got 3 comma pi over 3 plus 2 pi. Remember what we just said on the previous slide. If you're adding multiples of 2 pi to your angle, which is what we're doing, we're just adding 1 2 pi, we're going to end up at the same place. Because basically what we're saying is, okay, we're going to go out 3 units, we're going to go up pi over 3 units, and then we're going to circle around 1 full rotation from that pi over 3. So we end up right here at the same point. All right, last point that we're going to plot. 0 comma pi over 4. This point right here is just going to be at your origin because it has no distance. So anything with the 0 is just going to end up at your origin. Okay, so enough with plotting polar coordinates. Now let's figure out how can we go back and forth between both polar coordinates and rectangular coordinates. So we have formulas for these. First, let's go from polar to rectangular. So here is our formula. Our x-coordinate of our rectangular system is going to equal r, which is your distance, right? Your directed distance, times cosine of theta. Your y-coordinate is going to be r times sine of theta. All right, so let's convert the point, the polar point, 2 comma pi into rectangular coordinates. So we need to figure out what cosine and sine are of theta. So this is where you're going to have to go back to your unit circle. So if we were to look at our unit circle, we know pi is over here. So it's kind of a goofy point because it's pi, it's on one of the axes. But we know that pi is over here. So cosine theta equals -1 and sine theta equals 0. So when we plug in our information for here, we're going to plug in for x, we get r, which is 2, times cosine theta, which is -1. So we get the x coordinate of 2 times -1, which is -2. For y, we're going to get the point, or r, which is 2, and sine theta, which is 0. So we get the y coordinate of 0. So these have the same coordinates as the point -2, 0. So 2, pi in your polar coordinate system equals -2, 0. They are the same point. That just tells us in one system versus another. Okay, so now let's go from rectangular to polar. So to do this conversion, you're going to use your tangent inverse function. And what you're going to do is tangent inverse of y over x equals your theta, r squared equals x squared plus y squared. So we need to convert the point 1, -1 into polar coordinates. So we're going to take the point, or our y and our x, so we have tangent of -1, so our inverse function, we want -1 over 1. So you're going to need to look at your unit circle for this, or you need to figure out exactly where this is. If we were to graph tangent of that, it would be, ignore that graph. It would be, we're going down -1 units and over 1, so it actually would be over here. Because we want -1 for our y and a +1 for here. So this is a 45, 45, 90-degree triangle in the 4th quadrant. So that's going to be 7 pi over 4. So theta equals 7 pi over 4. Now we got to figure out what r equals. So r squared equals x squared plus y squared. So r squared is going to equal 1 squared plus a -1 squared, which is going to equal 2. So r equals the square root of 2. So now we've got the polar coordinates of square root of 2, 7 pi over 4. We have converted our rectangular coordinates of 1, -1 to square root of 2, 7 pi over 4. So you guys are going to get lots of practice with doing this in class. But that is it for today. We're going to go finish up this lesson over the weekend, but that is it for today. So I hope you guys enjoyed this and have a great day. Take care. Bye-bye.